All right, so our next speaker is going to be Joe Foster from the University of South Carolina, and he's going to speak on irreducibility criteria for polynomials with non-negative coefficients.
Cool, thanks for having me, and big thanks to the organizers. This is my first online conference. I'm sure it won't be the last at this rate, and I think it's gone pretty great so far, so thank you. So my talk is about irreducibility criteria for polynomials with non-negative coefficients. Okay, this is joint work with my advisor Michael Felicetta and my academic brothers Jacob Judera and Jeremiah Southwick. Okay, so I think I have exactly 20 minutes worth of stuff to say in 19.5 minutes, so I'm just going to fire through. So strap in. Okay, we'll start with a theorem attributed to Kohn that says if you take the decimal representation of a prime and make those digits the coefficient of an integer polynomial, then that polynomial is going to be irreducible. Okay, maybe the important thing to note here is that if we plugged in 10 into this polynomial, this quantity right here is going to be exactly that prime number. Okay, and this is the idea that we're going to be looking at further. Okay, so in 81, Bruja, Adlitsko, and Felicetta extended this idea so that the digits didn't need to be the decimal digits of a prime, but that could be the base b digits of a prime. Difference now, if we plug in f of b, we get this prime number appearing on the right-hand side. Okay, and we still have reducibility of that polynomial. In that same paper, with f of 10 being prime, they showed that the coefficients being the decimal digits was maybe not necessarily the important thing there. They showed that you could actually have coefficients up to 167 instead of just up to 9. And if f of 10 was still prime, then we'd still have irreducibility of f of x. Okay. And then in 88, Felicetta extended this further so that instead of just being bounded by 167, you could actually have 10 to the 30th times the leading coefficient. Again, f of 10 taking on a prime value being the key thing here. And then as just maybe an aside, if instead of bounding coefficients, which is what we're going to be talking about in this talk, you instead bound the degree, if you still take on a prime value, we can ensure irreducibility. Okay, so we do some work on the degree stuff as well that Felicetta started in 88. But this talk is primarily about bounding coefficients and looking at prime values. Okay, so continuing with bounding coefficients, then in 2014, Felicetta and Gross found this bound, this really large number that I won't attempt to say on camera. They said that if the coefficients were bounded by this and f of 10 was prime, then the polynomial would be irreducible. Not only did they find this giant number, they found an even bigger number, whereby if, again, f of 10 was prime and the coefficients were less than this bigger number, if it did turn out that that polynomial was reducible, then it had to have x squared minus 20x plus 101 as one of its factors. Okay, and then the most interesting thing about these bounds were that they were best possible. So if we increase these numbers by 1, we can find a integer polynomial with a coefficient of that size, f of 10 prime, and it reduces, okay, and breaks this theorem. Okay, so again, this is with f of 10 taking on a prime value. Continuing with the idea of replacing 10 with any integer, in 2016, Cole, Dunn, and Felicetta did precisely this for integers between 2 and 20. Okay, they found two bounds so that if the coefficients were less than the first bound and f of b was prime, then it would be irreducible. And they found a second bound so that if f of b was prime and the coefficients were less than the second bound, then they could say something about one of the factors that f had to have. Okay, and moreover, they proved sharpness of these bounds too. Okay, so enter myself, Jacob Judera, and Jeremiah Southwick, again with Felicetta. We have to do, we were told to do this for numbers bigger than 20, of which there are a couple. And we've done that. And this wall of text describes how that result looks. Admittedly, this isn't the prettiest thing you could read. So one of the goals of this talk is to make this more digestible and also explain to you the ideas, the tools required to get a result like this. Okay, so my first attempt at simplifying that wall of text is going to be the following. Let b be an integer bigger than or equal to 2, and then f is going to have non-negative integer coefficients, and f of b is going to be prime. Okay, throughout phi of n is going to be, phi sub n is going to be the nth cyclotomic polynomial. Okay, so there exists a bound m1 such that if all of the coefficients are less than this, then f is irreducible. There's a second bound so that if f of x has coefficients less than this bound and it reduces, then it has to have either a shifted phi3 or a shifted phi4 as a factor. There's a third bound, depending on b, depending on the value of b, it has to have phi of 3 or it has to have phi4. There's a third bound where if the coefficients are less than that, then it could have one or the other, but it has to have at least one. And then a fourth bound where if the coefficients are less than that and b is big enough, then it has to be divisible by one of 3 cyclotomic factors. Okay, so that's like a general outline of what we're going for. But the goal is to find criteria based purely on looking at coefficients where f is going to be a integer polynomial with non-negative coefficients taking on a prime value. Okay, we're trying to list criteria to determine the irreducibility of f just by looking at the coefficients. Okay, so all of the bounds that we find can be given explicitly in terms of b. Okay, so for example, for b bigger than 5, our first bound is given by this. Okay, and you can see it's purely determined by what little b is. Okay, if you plug in b equals 10, this bound agrees with the first bound that Felicetta and Gross found. Okay, so this is that first giant number, and it agrees with all of the bounds found with in the paper by Cole, Dunn, and Felicetta for b between 2 and 20. And so I commented on that they also determined that these bounds were sharp in their papers. This isn't something that we've worked on for all b in general, but it is something that, at least for this first bound, we strongly believe that it is going to be sharp, but that's not something that we've explicitly looked at just yet. Okay, so how does one go about obtaining this result? So we're going to show that if f of x has non-negative integer coefficients and it reduces, then it has to have a root in one of 4 locations on the complex plane. A region that we're going to define shortly, or it has to be at one of these shifted roots of unity. Okay. So the first thing we're going to do is we're going to find a bound on the coefficients so that if each coefficient is less than this bound, then f can't have a root in this region that I'm alluding to. And then we find 3 more bounds, one for each of the shifted roots of unity, so that if f of x has coefficients less than this bound, then it can't be divisible by one of the shifted cyclotomic polynomials. And then once we've got those 4 bounds, we compare them all and we get this sort of sliding scale that determines something about the irreducibility of f of x depending on what little b is. Okay, so we're going to start with finding this first bound on this region. So let's define this region that I'm alluding to. Okay, so as usual, let f be a non-negative integer polynomial with f of b prime. And suppose that it reduces. So suppose it reduces to g times h. Since f of b is prime, this is going to mean that one of g of b or h of b has to be plus or minus 1. So we're going to assume that it's g. Okay, so g of b is going to be plus or minus 1. Next, we consider a root bounding function, which is similar to the one given originally by Felicetta and Gross in their paper, and then it looks even more like ones given by Cole, Dunn, and Felicetta in their paper. And this is what we're going to use to define this region. I'm not going to talk too much about each of the factors of this function, but this is where this region is going to be coming from. Okay, so we define this certain function. Okay, so let C be the leading coefficient of G and R1 through Rn be its roots. Okay, and then we can show that these two quantities are equal. Okay, and so here you can see where this root bounding function is coming up. Okay, so we'll denote this common value by V. It turns out that this V is a non-negative integer. So it's either 0 or positive. If it's 0, then g of x, and therefore f of x, would have to be divisible by at least one of the shifted cyclotomic factors. Okay, so if it's non-zero, it has to be bigger than or equal to 1. As you can see from this product, that would mean that f evaluated at one of these roots has to be bigger than or equal to 1. And then this is how we're going to define our region. It's going to be all points on the complex plane that make our root bounding function bigger than or equal to 1. Okay, and this is what our region looks like that we determined. Similar ones, like I say, appear in the papers by Felicetta and Gross and Cole, Dunn, and Felicetta. But this is the one that we settled on that gave us a lot of tools to use for all b bigger than 20. And you can see the relation to these shifted roots of unity with this region. So of the entire complex plane, this is the only area that we're going to look at, and it all is based on this little b. Okay. So next we make use of a lemma that's going to allow us to find a bound on the coefficients, so that if f of x has coefficients less than or equal to this bound, then it can't have a root in this region that we've just defined. Okay, so this lemma gives us the existence of this bound. And what we do is we undercut this capital B by quite a lot. So we want a bound that's going to be only dependent on little b, and we don't find a trivial lower bound of this capital B here by any means, but we do. Our only goal is to get one that we can use and manipulate for all different values of little b, and that was our only concern. So this script b that we do settle on is by no means a good bound. It's not the best bound, but it's one that allows us to do a lot of work. Okay, so this lemma gives us the existence, and then we do some approximations, and then we have a bound on the coefficients such that if f has coefficients less than this bound, it can't have a root in that giant area that I've just shown. Okay, so now we need 3 more bounds, one for each of the shifted roots of unity. Okay, so let's look at what f would have to look like if it was divisible by one of these cyclotomic factors or cyclotomic polynomials. Okay, each of them is a quadratic that we can write in the form x squared minus px plus q. And as you can see, if f was divisible by x squared minus px plus q, since f has non-negative coefficients, the coefficients of its other factor have to satisfy this inequality. Okay, so based on this inequality, we can define a sequence. And this sequence is going to be really key in helping us find a bound. And as such, we found it particularly useful to write the elements of this sequence in this form instead. This just gave us a lot more flexibility in our calculations and algebraic manipulations. So this is what we have. And so this sequence beta j starts off positive and increasing. But as you can see, just the existence of this factor of sine, you can see if you make j big enough, this is going to be negative, and beta j is eventually going to be negative at some point. So we're going to look at that first initial positive chunk, and we're particularly interested in the largest value that beta j is going to attain there. Okay, and it's going to we're going to denote this location by a capital J, and it's either going to be the very last positive number it takes before it turns negative, or it's going to be the second last positive value it takes before it turns negative. Okay, and this is the crucial value here. So we're interested in the smallest value that the largest coefficient of x can be. And we show that this value is given by this. So 1 minus p plus q times this beta sub capital J. Okay, and so p and q come from the shifted cyclotomic factor, and those values are determined completely by what little b is. And beta j comes from those coefficients, and therefore beta j is completely determined by what little b is. So we have a bound on these coefficients that is given explicitly in terms of little b. Remember, little b is the point where we're going to say that f is going to take a prime value. Okay, so if the maximum coefficient of f of x is equal to this, then our second factor here, h, takes on a composite value at x equals b. So then when we throw back in our condition that f of b needs to be prime, then if all of our coefficients are less than this bound we've just found, then we cannot have f divisible by one of these shifted cyclotomic factors. Okay, so that's where, that's a very, very quick description as to where these bounds come from. But the important thing is we found 4 bounds: BB, BB3, BB4, and BB6. If we had a BB8, that would be great, and I could insert a Star Wars joke, but I can't. Let f of x be an integer polynomial, have non-negative coefficients, and f of b be prime. Then what we've just found is a bound such that if the coefficients are less than that, we can't have a root in that region we defined. If the coefficients are less than BB3, then f of x can't have a root in common with the shifted third cyclotomic polynomial. And likewise for BB4 and BB6, if f of x has coefficients less than these bounds, then we can't have phi4 or phi6 as a factor. Okay, so of the 4 locations where we said f had to have a root, we found criteria so that we can say f can't have a root there, and therefore that's going to give us irreducibility. Okay, so we need to put all that together, and then this is where I can now hopefully explain what that big wall of messy text said in our giant theorem. Okay, so let f of x, as usual, be an integer polynomial with non-negative coefficients that takes on a value at x equals b, a prime value at x equals b. Okay, and let a be the maximum coefficient of f. The bounds compare in 3 different ways depending on values of little b. Between 3 and 5, BB3 is less than BB4 is less than BB is less than BB6. Between 6 and 69, BB4 and BB3 swap places. So that's the only change here. And then for b bigger than 69, BB6 and BB swap places. And this is the relationship between the bounds that persists for all higher values of little b. Okay, so these are our three cases. And so the result is then that for b between 3 and 5, if the largest coefficient is less than BB3, then f of x is irreducible. If the largest coefficient is less than BB4 and f of x is reducible, then it has to be divisible by the shifted third cyclotomic polynomial. And if it's less than BB and it's reducible, then it has to be divisible by one of either the third shifted cyclotomic polynomial or the fourth shifted cyclotomic polynomial. Okay, so between 6 and 69, the statements are pretty similar. Obviously, because BB4 and BB3 swap places, the first factor that we could possibly have is now going to have to be phi4 instead of phi3. And then for b bigger than 69, again, it's very similar, but BB and BB6 have swapped places, and then that also gives us our 4th bound so that we can also talk about when f is divisible by the 6th shifted cyclotomic factor as well. Okay, and so then this is what we've proven. Okay, so based on a single prime value that f takes, the coefficients completely determine whether or not this polynomial is going to be irreducible, okay, depending on where that prime value happens, okay, just by looking at the coefficients. And I think that is it with 30 seconds for questions. I'm sorry if that was too fast. I will happily answer them in the break room if we've not got time, but there we go. Thanks for listening.
All right, thank you very much for a nice talk. We probably have time for a couple quick questions. Are there any?
Uh, can you go to the slide 5? Just want to take a look. Yeah, I think it did mention these two numbers are sharp, right? These two bounds.
Yeah, these bounds are sharp.
Okay. Another request. Can you send these two numbers to me? Maybe I'll put as a password for my next Zoom meeting.
Yeah, I can do that. I'll give it to you written like this.
This one better?
Yeah.
Okay, I'll take that. Yeah, that will be the best password.
Other questions? All right, let's thank the speaker again.